Hello everyone, I am Mohan Naik, Assistant Professor, Triple Department, Marri Laxman Reddy Institute of Technology and Management. Today I am going to discuss the topic DC Theorems. So in this theorem, I am going to discuss Thevenin's theorem and superposition theorem. First we are discuss the Thevenin's theorem. Statement of Thevenin's theorem. In any linear bilateral network, a circuit is consisting of n number of independent sources and n number of passive elements. That entire network can be replaced by a simple circuit. That circuit is consisting of a single voltage source in series with the single resistor. That equivalent resistance is called as Thevenin's equivalent resistor. So this is a statement of the Thevenin's theorem. Next, procedure for Thevenin's theorem. Procedure of a Thevenin's theorem. Step number 1. Identify the load resistor. Identify the load resistor across the two terminals, that is A and B. So if any circuit is, the given circuit is like this, if circuit is consisting of n number of resistors, that is, and sources, and this one is considered as load resistor. So first step is remove this load resistor. Remove the load resistor. And step number 2, find the Thevenin's voltage across the open terminals. Wherever we remove the load resistor, name it as A and B terminals, and across the open terminals find Thevenin's voltage, that is the open circuit voltage. This voltage is also called as, this open circuit voltage is also called as Thevenin's voltage or open circuit voltage, VOC. That is about second step, step number 2. Next, step number 3, find the Thevenin's equivalent resistor. Thevenin's equivalent resistor. When we calculating the Thevenin's equivalent resistor, all the independent sources are replaced with their internal resistances. If any voltage source is present, that voltage source is replaced with a short circuit, and if any current source is present in the circuit, that current source is replaced with the open circuit. For example, as circuit is consisting of a voltage source in the circuit, when we are calculating the Thevenin's equivalent resistance, then this source can be replaced with a short circuit. This source is replaced with a short circuit. That means their internal resistor is R equal to 0. Internal resistance of voltage source is R equal to 0. 0 means itself it is a short circuit. If any current source is present, this current source is replaced with their internal resistance. So if current source internal resistance is R equal to infinity, the resistance of open circuit is infinity. So make it as open circuit. If current source is present in the circuit, that current source is replaced with a open circuit. That is step number 3. And step number 4, draw the Thevenin's equivalent circuit with the V Thevenin's and R Thevenin's, both are connected in series. So that is the step number 4. V Thevenin's in series with the R Thevenin's. This circuit is called equivalent circuit. Thevenin's equivalent circuit. Thevenin's equivalent circuit. And again reconnect the removed load resistor. In step number 1, we removed the load resistor. So same load resistor can be again reconnected at the across the Thevenin's equivalent circuit. Then you find the load current IL by using the formula VTH by RTH plus RL. That is a procedure for, that is a step number 5. That is a step number 5. Find a load current IL by using this formula. IL equal to V Thevenin's by R Thevenin's plus RL. Example for the Thevenin's theorem. Determine the current I in the circuit shown by using Thevenin's theorem. So this is a given circuit diagram. In this circuit diagram, we need to find the Thevenin's voltage, and also we calculate the Thevenin's resistor, and we also calculate the current through the 2 ohm resistor. In this circuit, 2 ohm resistor current is there is a load current. Now for that, step number 1 procedure is step number 1. Remove the load resistor. Where the current load current is we are calculating itself, that resistor is called as load resistor. So remove this 2 ohm resistor and redraw the circuit. Remove the step number 1 is remove the load resistor. Remove the load resistor, that is 2 ohm resistor. That is 2 ohm resistor. And again redraw the circuit diagram. Plus minus 35 volts is a voltage source. This is 3 ohm resistor, and we remove this load resistor. Remove this load resistor and 4 ohm resistor, and second source is this. Another source is 40 volts source. 40 volt source. Now name it as A and B. These open terminals as A and B. And step number 2. Calculate the Thevenin's voltage. Thevenin's voltage across A and B terminals. Wherever we remove the load resistor, across those terminals we are calculating the Thevenin's voltage, that is the V Thevenin's. That means here VTH or VOC. VOC, both are same. VOC. So how we calculate the Thevenin's voltage? By applying a node analysis. By applying a node analysis method, node equation at this node. This node is considered as V, and that is also called as VTH. This node name is, node is nothing but it is a combination of 2 or more than 2 elements connecting point, that is called as a node. So more than 2 elements, this node is considered as principal node. If the node is formed with more than 2 elements, that node is called as principal node. Or any simple 2 elements are connected at point, that node is called as simple node. So this is a principal node, VTH. So first we write the node equation. First we need to write the node equation. The node equation is VTH is the unknown voltage, and 35 volts and 40 volts are the known voltages. So this voltage, VTH voltage, is considered, assumed as it is a higher potential, and we write the node equation. So we apply the node equation at VTH, then the equation will become VTH minus 35 by 3 plus VTH minus 40 by 4 equal to 0. And simplify this equation. VTH is common from both the terms, 1 by 3 plus 1 by 4, and remaining terms are 35 by 3 plus minus 40 by 4, it is equal to 0. Then we get the VTH value, that is the open circuit voltage, that is the Thevenin's voltage, that is 37.5 volts. VTH value is 37.5 volts by applying a node equation. Next we need to calculate the step number 3. Step 3. Calculate RTH, that is a Thevenin's resistor across open terminals A and B. Open terminals A and B. The given circuit is, this first source is 30 volts. First source is 35 volts, and resistor. This is the open terminal. Second resistor, and this source is 40 volt source, and remaining resistor values are 3 ohm and 4 ohm resistors, 3 ohm and 4 ohm resistor. So condition for the RTH is, when we calculating the RTH value, if any source is present in the circuit, that source is replaced with their internal resistance. So these two resistors are voltage sources. So voltage sources are replaced with short circuit. Voltage sources are replaced with short circuit. So these two sources are make it as short circuit. These two are short circuit. And now calculate the total resistance, that is R total, RTH, that is R total, A and B terminal, across A and B terminal, RTH. So this value is, so when we make it as short circuit of both the sources, then this circuit is become, both the resistors are in parallel, that is a 3 into 4 by 3 plus 4, 3 plus 4, then it is a 12 by 7 ohms. 12 by 7 ohm is a RTH value, that is a Thevenin's resistor, 12 by 7 ohms. Now step number 4. Step number 4. Draw the Thevenin's equivalent circuit. Draw the Thevenin's equivalent circuit with the combination of VTH and RTH. The Thevenin's equivalent circuit is this one. So VTH value is 37.5 volts and RTH value is 12 by, that is a 1.714. 12 by 7, that is 1.714 ohms. This is a Thevenin's equivalent circuit. And at last, add a removed load resistor. So across the Thevenin's equivalent circuit, the resistor value is 2 ohm. The load resistor is 2 ohm resistor. Now these two are connected in series. The resistor, the RTH value, RTH and RL both are connected in series, and we know the voltage value 37.5 volts. Only unknown is current through the circuit. That current is also called as load current. So why? Because series circuit, in series current is same, so load current is same as RTH current, both are same currents. So to find the load current, IL equal to V by R, according to the Ohm's law, V by R. So we have two resistors, both are connected in series, so VTH by RTH plus RL. So VTH is 37.5 and RTH is 1.714 plus RL is, load current is 2 ohms. Then the total current is load current is 10 amperes. So load current is 10 amperes. So in this way we are calculating the load current in the circuit. The application of the Thevenin's theorem is, by using Thevenin's theorem, we can reduce the size of the circuit. If the circuit is consisting of a large if the network is consisting of a number of voltage sources and number of passive elements, that entire network can be replaced with a single source and single element, both are connected in series. So that is a Thevenin's equivalent circuit. So we can reduce the size of the circuit, and we can calculate the load currents, and we can calculate the voltage or current or power across any element, so by using the Thevenin's theorem. So next, superposition theorem. In any linear bilateral network consisting of two or more than two independent sources, the algebraic sum of the individual responses are equal to the overall response. When we are calculating the individual responses, the sources are replaced with their internal resistances. That is, voltage source is replaced with the voltage source is replaced by short circuit, and current source is replaced with the open circuit. This is the statement of superposition theorem. So procedure for superposition theorem. Select one independent source and deactivate all other sources. If the circuit is consisting of n sources, you can select any one source is active and all other sources are deactivated. So that means replaced with their internal resistances. And step number 2, find the current or voltage in the required element due to the present source, that is the active source, and repeat for the each independent sources and add algebraic of all the individual results, that is called as algebraic sum of the total responses. That means if the circuit is consisting of two sources, then the response across the resistor, suppose this resistor name is R3, R1, R2, this one is V1 and this one is V2. The response across this R3 is overall response. First it is considered as I, overall response is I. And due to this voltage source V1 and absence of this source V2, that current is considered as I1. And V2 is present and V1 is absent, that response is considered as I2. These two are the individual responses. These individual responses are equal to algebraic sum of the individual responses are equal to overall response, that is a superposition theorem. So we have a limitations for this superposition theorem. We cannot directly calculate the power value by using the superposition theorem. So this theorem cannot applicable for power calculations. We can calculate the voltage, current, but we cannot calculate the power by using the superposition theorem. And also this theorem is not applicable for non-linear elements like diodes, transistors or semiconductor devices. We cannot apply the superposition theorem. Becomes the time consuming for the circuits with many sources. If the source is consisting of more number of sources, so while we are calculating the individual responses, it takes a longer time compared with any other theorems, that Thevenin's theorem or Norton's theorem. So it will take some more time for the calculation of values, right?